So let us continue our discussion with the half-life period. So it is denoted as T half or T 0.5. So half-life period can be defined as the time required for disintegration or decay of one half of the initial amount of the radioactive substance. So it is called as the half-life period. So when the time t is equal to t half, that is half-life period, so then n is equal to n naught divided by 2. So let us substitute these values in equation number 1. So that is previously we have did. So if you substitute the values, so that is t is equal to t half and n is equal to n naught divided by 2. So in the equation number 5. So you will get, so lambda is equal to, so that is 2.303 divided by, so t half into log of n naught divided by n naught divided by 2, or that is equal to 2.303 divided by t half into log 2. So or if you simplify this, so that is equal to 2.303 divided by t half into 0.3010. Okay, so that is equal to 0.693 divided by t half, or t half is equal to 0.693 divided by lambda. Okay, so this is the expression for the calculation of half-life period. So as the lambda is a constant for the radioactive element or a substance, its half-life period is also a constant, and it is independent of the amount of the substance which is initially present. Okay, so each nuclide has a fixed value of half-life period, so which can be used to identify the nuclide. So here, so we have some problem on the calculation of the decay constant of carbon having the mass number 14 and atomic number 6, whose half-life period is 55577 years. So that is 5577 years. Okay, so we have to calculate the decay constant. So that is lambda is equal to 0.693 divided by t half. So that is 0.693 divided by the half-life period of the carbon is given. So that is 5577 years. So therefore the decay constant for the carbon 14 is 1.242 into 10 power minus 14 per year. Okay, so in the next problem, so the disintegration constant of a radioactive isotope is 4.8 into 10 power minus 9 per second. So we have to calculate the half-life in the years. Okay, so the decay constant has been given, that is lambda is equal to 4.8 into 10 power minus 9 per second. Therefore the t half, we know that the t half is equal to 0.693 divided by lambda. So that is equal to 0.693 divided by 4.8 into 10 power minus 9 per second. So if we calculate, so you will get 1.44 into 10 power 8 per second. If you convert it into years, that is 1.098 into 10 power 2 year. So let us discuss about the radioactive equilibrium. So let us consider a radionuclide A. So that is a parent nuclei having a long half-life. So it undergoes decay to form the daughter nuclei with a short half-life. Initially, the number of atoms of A undergoing decay is very large, and the number of atoms of B in the mixture is very small. That is, the concentration of the daughter nuclei is will be low. Okay, so with the as the disintegration continues, okay, with the time, so there will be a decrease in the number of atoms of the parent nuclei A with the increase in the number of daughter nuclei B. Okay, so we know that when the reaction proceeds, the concentration of the reactants will goes on decreases and the concentration of the products goes on increases. So similarly, in case of radioactive disintegration, so the parent nuclei A, so when it undergo disintegration or when it undergoes decaying, so it forms the daughter nuclei B. So as the disintegration proceeds, so the concentration or the number of atoms of parent nuclei A decreases and the number of atoms of daughter nuclei B increases. Okay. So in such cases, a stage is reached. So when the rate of decay of the daughter nuclei, the parent nuclei becomes equal to its the rate of formation. Okay, so the rate of, that is the rate of decay of daughter nucleus becomes equal to its rate of formation. Okay, so a state of radioactive equilibrium, or we can call it as a steady state, is said to be established. So the term equilibrium is not preferred, okay, because the process of the decaying of A, parent nuclei A, to B, daughter nuclei B, is irreversible. Okay, so at a steady state, the parent nuclei A is converted into the B and B is disintegrates into C. So at a radioactive equilibrium, or we can call it a steady state, all the radioactive elements disintegrate at the same rate. So that is, so the disintegration of A into Na, disintegration, that is lambda B of Nb into lambda C of Nc, etc., are the rates of the decaying of the elements A, B, C, etc., respectively. So then the lambda into A of Na is equal to lambda into B of Nb is equal to lambda C of Nc. Okay, so at radioactive equilibrium, so the amounts of all the nuclides undergoing the decay remains the same. So for any two nuclides in the mixture, so it is given by, so lambda A into Na is equal to lambda B into Nb, or the lambda A divided by lambda B is equal to Nb divided by Na. So since the decay constant is inversely related to the half-life period of the radioactive nuclei, so the above expression so can be written in the form Nb minus Nb divided by Na is equal to T half of B divided by T half of A, or Na by Nb is equal to T half of A divided by T half of B. Okay, so this equation is useful in the calculation of half-lives of the radioactive nuclei. So here in this graph, so you can observe that, so as the reaction proceeds, okay, so we have plotted the time versus the rate of disintegration. Okay, so the parent nuclei A disintegrates into B, okay, and the B daughter nuclei disintegrates into C. So what a state of the radioactive equilibrium or the steady state is established. Okay, so when the rate of decaying of the B, okay, that is daughter nuclei, becomes equal to its formation. So this is the formation of B and this is the disintegration of B. So when the rate of formation of B becomes equal to the rate of disintegration. So then that point is called as the radioactive equilibrium or the steady state. Okay. So next let us move on to the radioactive series. So the nuclides with atomic number greater than 83 are unstable. So we know that any element having the atomic number greater than 83 is said to be unstable, and it will undergo radioactive decay, emitting either alpha or beta particles. So as a result, a new element called as the daughter element is formed. So if the daughter element is also radioactive, so it becomes the parent element and undergoes decay and forms another daughter element. So this process will go on till a stable element of the isotope of either lead or bismuth is obtained. So until a stable isotope of lead or the bismuth is obtained. Okay, so the process of disintegration of the radioactive element continues until a stable element is formed. So that is either lead or bismuth. So the radioactive series, so it can be defined as the series of changes which takes place by the emission of either alpha or beta particles from radioactive elements up to the formation of a stable element is called as the radioactive disintegration or decay series. Okay, so there are three naturally occurring radioactive elements. So that is thorium, uranium, uranium-235 and uranium-238. So they have long half-lives. All other unstable heavy nuclides are formed by the radioactive decay of one of these nuclides. Okay, so thus the thorium-232, uranium-235 and uranium-238 constitute the parent nuclide of the three natural radioactive series. So these series are referred to as the thorium series, actinium series and uranium series. So after a prominent member in each series, neptunium series is also an artificial radioactive series and starts with neptunium 23793. So first let us see the first series, so that is thorium series, or it is also called as the 4N series. 4N series. So this series starts with the thorium 232 and ends an element with lead 208. So it is known as the 4N series because the mass number of the members of the series are divisible by 4. Okay. So the next series is the neptunium series, which is called as the N4N plus 1 series. So the synthetic transuranium element, so a new series of neptunium series has been added. So it is artificial series of nuclides. So it starts with the neptunium 237 and the end with the bismuth 83, and it is known as the 4N plus 1 series. So because the mass number of the members of this series when divided by 4 will give a remainder of 1. So that's why this series of neptunium series is called as the 4N plus 1 series. So the third series is the uranium series, which is 4N plus 2 series. So it starts with uranium 235 and ends with the lead 206. So it is also known as 4N plus 2 series because the mass numbers of the members of this series are divisible by 4 and gives a remainder 2. So therefore the uranium series is also known as 4N plus 2 series. So the next series is the actinium series, which is also called as 4N plus 3 series. So it starts with uranium 235 and ends with the lead 207. So it is known as the 4N plus 3 series. So because the mass number of the members of this series, when divided by 4, they give a remainder of 3. So here you can see a series of the rate of disintegration of the elements. Okay, so thorium 232 disintegrates by emitting an alpha particle. So it reduces to the Ra 228 with mass number 228, and so this Ra, so it emits a beta particle and it's converted into the AC actinium 228, and this actinium emits a beta particle and it gets converted into the thorium, and this thorium will emits alpha particle. So the radium, so when it emits alpha particles, so it is converted into the Rn, that is radon, and when the radon undergoes disintegration by emitting an alpha particle, so it forms PO, that is polonium. So polonium undergoes disintegration by emitting the alpha particle to form the lead. So this lead further undergoes disintegration by emitting the beta particle to form the bismuth, and the bismuth emits a beta particle to form the polonium. So the polonium, so it emits an alpha particle to form the lead with atomic number 82, so which is the stable nuclei. Okay, so this is the thorium series. So the thorium undergoes the series of disintegration and finally it forms the stable nuclei, so that is lead nuclei. Okay, so next one, so let us see the neptunium series. So that is the neptunium with mass number 237 and atomic number 93, so emits an alpha particle, so to form, so that is the proctactinium, and this proctactinium after emitting a beta particle, it's converted to uranium 233. So uranium 233 disintegrates by emitting an alpha particle to form the thorium 229, and this thorium undergoes that is disintegration by emitting the alpha particle to form the radium, and radium undergoes disintegration by emitting the beta particle to form actinium. So this actinium undergoes disintegration by emitting alpha particle to form the francium. So the francium emits alpha particle and it forms the AT. So that is astatine. So this astatine emits alpha particle to form the bismuth. So this bismuth emits an alpha particle to form the thallium, and this thallium disintegrates by emitting the beta particle to form the lead. So the lead undergoes disintegration by emitting the beta particle to form the stable bismuth nuclei. So next let us discuss about the uranium series, that is 4n plus 2 series. So the lead with mass number 206 and atomic number 82. So that is so in the uranium series, so that is 4n plus 2 series. So you can see here, so the uranium 238, so when it emits an alpha particle, it undergoes disintegration to form the thorium. So thorium when emits a beta particle, so that is the thorium when emits a beta particle, so it will form the Pa. So that is the atomic number, so that is 91, that is proctactinium, and when proctactinium emits a beta particle, it forms uranium 234. So when the uranium 234 emits an alpha particle, it again forms the thorium with a 230 mass number. So thorium when emits an alpha particle, it forms the radium. So radium when emits an alpha particle, it forms the radon. So when radon emits an alpha particle, so it forms the polonium. So when polonium, if it emits an alpha particle, it forms the lead. Okay. So if it emits a beta particle, it forms the AT. Okay, that is astatine. So if lead emits an alpha particle, it forms the bismuth, or when the astatine, so the emits an alpha particle, it will also form the bismuth. So when bismuth emits an alpha particle, it forms the thallium, and if bismuth emits an alpha particle, it forms the polonium. So the thallium, okay, so when it emits a beta particle, it forms the lead. So similarly, when polonium emits an alpha particle, it forms the lead. So when the lead emits a beta particle, it forms the bismuth. So this bismuth when emits an alpha particle, so it forms the thallium, and the bismuth if emits a beta particle, it emits the polonium. So if thallium emits a beta particle, it forms the stable isotope of lead, that is the mass number 206 and atomic number 82. So similarly, when bismuth emits an alpha particle, so it forms the lead also. So therefore, a stable isotope will going to be formed. So let us come to the last series, that is octenium series, that is 4n plus 3 series. So in case of octenium series, the uranium 235 92 emits an alpha particle to form thorium. Thorium emits a beta particle to form the procractinium. So in the procractinium emits an alpha particle, it forms the actinium. So actinium when emits a beta particle, it forms the thorium. So thorium when emits an alpha particle, it forms the radium. So radium after emitting an alpha particle, it forms a radon. So radon emits alpha particle to form the polonium. Polonium emitting alpha particle, it converted into the lead, okay, with the atomic number 82. So this lead emits a beta particle to form bismuth with atomic number 83. So this bismuth is also an unstable, it emits an alpha particle to form the thallium. So thallium when emits a beta particle, it forms a stable lead nuclei with atomic number 82 and mass number 207.